Good morning, folks. This is the course in mechanical vibrations, and I already made the presentation in class yesterday, but I'm also recording what I said and posted on YouTube. Now, the thing that I'm going to do in this recording is I'm going to avoid number one, going through the course syllabus, because that was already done in class, and the course syllabus is posted on Brightspace. You can go check it out. But I'm going to be mostly talking about motivation behind going through a vibrations course. And towards the end, I'm going to say a few words about how to solve very simple differential equations that is actually a must in a course like this. Now, vibration and sound are closely related. Okay. And basically, a sound is the vibration of a source which is transmitted through the air molecules into a target. Okay. So essentially, vibration is the disruption of something from its equilibrium point, as you'll see it in a minute. Now, what I said doesn't seem to be my statement initially, but you'll see what I mean by this disruption that I'm talking about. Now, let's take this situation where you are mostly familiar with, and we have a suspension system here. Essentially, it is a four-bar linkage. You can see that we did this in the CAE course last summer. So we have link one, link two, which is the tire, link three, and link four, which is essentially the chassis of the car. Now, obviously, if you go over a bump, this starts vibrating up and down or in some other direction. And this, at the end of the day, is a very complicated setup, but we're going to replace it as a first attempt with a, a spring and a mass. Don't let this thing fool you. This spring is not the spring that you see on the left-hand side. Essentially, vibration is taking place because there is a mass and the mass wants to move and something disrupts it. And in this case, happens to be the force in the spring, which is disrupting it and trying to make it go in the other direction. Now, uh, the mass, in some sense, is the mass of this thing on the left side, but the spring is coming because the whole thing on the left-hand side, the whole suspension system acts as a disruptor, uh, as a fancy spring. For example, if you put a load here, a small load, if you push the tire up a little bit, this setup, the suspension, resisted, of course, through the structural component that you see here and through the spring that's sitting here. So that disruptive force is represented by the spring there. What you see on the right-hand side is a very elementary, basic representation of an oscillatory system that you see on the left-hand side. Now, keep in mind that uh, another way of saying that vibration is a layperson's explanation, but works well. Vibration is basically an object is trying to move back and forth, and that's what you refer to as oscillation or vibration. Okay. Another way of looking at this thing, and this is a very good explanation, is vibration is the exchange of energy between potential energy and kinetic energy. And if you wonder what does that mean, suppose we have a pendulum here that is hanging from the ceiling and there's a ball attached to it, and we move the ball, for example, to the right to a given height. Now notice that when you do that, at this given height, it has a potential energy due to gravitation. That's why when you release it, it tries to go back to where it is. It's going to release that energy that I'm talking about, potential energy that I'm talking about. So when you release this thing, the ball will move back to its equilibrium position. Okay. At this equilibrium position, it gains the maximum velocity or maximum kinetic energy. but no potential energy, because from that reference point, it has lost all of its potential energy, and therefore the potential energy on the right hand side at that initial position when you raised it is going to get changed to a kinetic energy, which is velocity velocity. And as long as there is no friction in the ideal situation, this ball will uh, 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 oscillate about this equilibrium position back and forth. Now, keep in mind that there is a mass and there is a resisting force. And the resisting force in this case is not actually a spring, is actually the weight of the object, which is the ball, which is due to gravitational effect. So it's the gravity that brings it down. It's the gravity that opposes the motion of uh, opposes the oscillation. Okay. Now let me go back to the vibration that comes about in the form of noise. So basically, if you look at the speaker, uh, uh, there is a diaphragm which vibrates, and let's not worry about how it vibrates or why it vibrates on the other side. And this vibration of the diaphragm is going to make the air molecule immediately next to uh, the diaphragm to move a little bit. Now, that doesn't mean that this air molecule will start moving and it goes meters, etc. It just hits another air molecule, and that other air molecule feels it. And then the second air molecule hits the third air molecule, and that third molecule feels it. So essentially, there is a disturbance that is traveling from the air diaphragm all the way. It's a disturbance. It is a wave that travels from the uh, uh, speaker diaphragm through the air by this tiny little bit of motion of air molecules hitting each other all the way to your eardrum, where there is another diaphragm is involved in your ear, and that starts to vibrate. Okay, I'm not worried about what happens to the right of the uh, speaker diaphragm or to the left of the eardrum molecule, because that is not uh, our purpose here. So essentially, when we talk about sound, there is a source, which is, for example, the speaker diaphragm. There is air molecules involved, which make this travel, this disturbance wave or stress wave travel. There's a medium involved, and then there's the eardrum or the target. Okay, it's also all vibration. Okay, because it starts with the source vibrating as a mechanical system, it goes to the eardrum vibrating as a mechanical system, so it is vibration. Okay. Air molecules themselves do not travel through this medium, but they keep hitting the fellow next to it, and it's a disturbance that's traveling. Okay, one of the most common units of measuring the uh, oscillation or vibration is in terms of frequency is called hertz. Hertz is the number of full cycle that are created in 1 second. Okay. Now, for noise purposes, very often people also refer to a different unit, and uh, now there is another unit of frequency that we're going to be discussing later on, and it's called radians per second. But maybe in the class, the way it sounded, I was trying to say that if another unit of frequency is decibel. That is not true. Decibel is not a measure of frequency. It is the measure of intensity of sound. And human being is, first of all, is limited in hearing certain levels, and we are restricted to, uh, 0 to 120, 130 decibel in terms of uh, intensity of sound, not frequency. Frequency, it's limited between 20 hertz and 20,000 hertz. So please do not misunderstand that dB is a unit of frequency of a sound. It is intensity. Okay, the way it may have sound, the may have uh, uh may have appeared to you in the lectures that I was saying this is frequency. It's not. dB is not frequency. Now, this 20,000 hertz is not cast in stone, but it can vary. For example, as you can see here, uh, could be 15,000, 17,000, something like that. Now, when it comes to vibration, let me see where the general setup of this whole concept is concerned. First of all, in your first year engineering curriculum, you took the statics course, okay, which is essentially the uh, things that think about it as don't move. That is not quite correct, but anyway, static. Then it came the second course in your curriculum in the first year, which was dynamics. Okay, now, vibration is part of dynamics, okay? And a subset of vibration is noise on acoustics, okay? This course is primarily about vibration as a whole and does not go into essentially details of the noise and acoustics. We have a separate course which deals with that. Now, something that's closely related to this business of vibration is controls. How do you control vibration? Because without being able to control it, it's kind of useless. Vibration can be very detrimental. Okay, this course is, as I mentioned, right there. What if it's not controlled? You're all familiar with this picture. This is the Tacoma Narrows Bridge, which went under severe vibrations back in the 40s, only a few days after inauguration, and eventually it collapsed. Okay, and I'll show you a video of this, which is very instrumental in understanding what's going on to some extent. And the other one is this Hawaiian airline aircraft, which lost part of its fuselage, and unfortunately, two people perished. And this was also involved with cyclic loading. Although uh, the explanation for what you see on the right hand side is different from what you see on the left hand side. So let's actually watch this thing together.
As you can see, this bridge was exceptionally long and narrow, over half a mile long, only 39 feet wide. It lasted just 4 months. During construction, we see the steel girders, 8 feet tall, which were supposed to stiffen the bridge against bending. However, some up and down vibration was observed during the entire useful life of the bridge. Here's opening day. On November 7th, the bridge suddenly went into a twisting motion. The wind speed was a steady 42 miles per hour. This was enough to keep the bridge oscillating in one of its natural modes of vibration with a period of 5 seconds. A professor of engineering went out to see what had happened. He's coming back, walking with some difficulty along the nodal line, which is the center stripe of the roadway. It's remarkable that the girders were this flexible. This is photographed at normal speed. However, a collapse was inevitable after a little more than an hour of this. The car had been abandoned earlier. No one was injured in the whole affair. However, a small dog in the car was frightened and was afraid to come out, and he perished along with the bridge. The bridge was rebuilt using a stiffening truss instead of girders. The new bridge is completely stable.
It was cyclic loading was also involved, but it was not due to resonance. As the plane lands and take off and flying in the air, the cabin has to be pressurized and depressurized, pressurized, depressurized. And this cyclic loading eventually made the certain cracks between the rivets to propagate. And of course, as a lot of these are connected to each other, essentially it loses in structural integrity. So the situation there, although due to cyclic loading, was because of the fatigue crack propagation. Okay, not resonance. All right, let's move on. Now, you have to understand that vibration is not always something that is detrimental. Uh, for example, when you want to, it can be such as what I just showed you, but it can also be used for uh, as an example, shaker tables where you separate the different size fruit, different size coins, etc. Therefore, vibration can be undesirable, as you saw on the in the Hawaiian airline, for example, situation, or the Tacoma Narrows Bridge, or desirable because we actually want to use it for a certain purpose. Another example is for electric shaver. Electric shaver inside of it is something that actually shakes like hell, and that makes actually the razor cut your you know beard, I suppose. Okay. Now let's look at some people who actually contributed to the concept of vibration, either indirectly or directly. Of course, uh, Galileo was the first one who actually uh, got interested in this and tried to come up with some explanation for things which are almost uh, related to vibration. And then Isaac Newton, of course, he was responsible for the equations of motion and dynamics, and of course vibration is part of dynamics, although he did not specifically get into the subject of vibration per se, but his contribution, of course, is there. Robert Hooke, who was a contemporary of Newton, is known for its Hooke's law or the stiffness of the spring. Once again, uh, springs pop up everywhere, or the stiffness pops up everywhere in vibration, and therefore indirectly his name comes up. Lagrange, although we don't do it in this course, we don't cover the concept of variational principle. But Lagrange and one of the other contemporaries doesn't come to me. The name doesn't come to me right now. They came up with whatever Newton was doing, but in the form of variational principles. Now, we don't cover that except for certain limited amount of energy principle. We're not going to cover what he's doing. In a more advanced course, you're going to see a lot more about what Lagrange did and his approach to solving dynamics problems. And of course, the big guy, Euler, was responsible for pretty much everything, including some of the things that we use in vibration. Lord Rayleigh was more recent, is about 100, 200, 150 years ago. He was one of the modern people who did actually contribute directly to vibration. And finally, Fourier. Without the work of Fourier, we will not be able to explain a lot of stuff that we are going to be doing in this course and vibration in general. Now, let's talk a little bit about this business of frequency of fre frequency in terms of hertz, for example. Uh, Now, what I've done here is to draw three very clean sine curves or sinusoidal curve, can be sine or cosine. One of them has, in 1 second period, has three full cycles. So you go from here, here is from here to here is one full cycle, and then two full cycle, and then third cycle. Okay, so we say that this signal has a frequency of 30 hertz because in 1 second it repeats completely three times. Here's a sine curve which actually repeats itself 6 times in 1 second. And there is 12 times in 1 second. So that's why we call this thing a 3 hertz signal, 6 hertz signal, 12 hertz signal. So basically, in terms of hertz, the frequency is the number of repetitions in 1 second. Okay. Now, the period is a no-brainer. The period is, for example, the distance in measured in time between two peaks or two troughs or two locations, which things get repeated. For example, you can see that the period here is 1/3 of that, 1/6 of that 1 second, etc. So if you have the frequency and you flip it, frequency in hertz, so be careful, frequency, and you flip it, you get the period or the other way around. Okay. There is another unit of frequency which is radians per second or circular frequency, and we're going to be using that a lot, okay? Because the derivations are pretty much done in terms of not this hertz, in terms of the circular frequency, which is radians per second. Okay. Let's go back to that sine curve. From our elementary math classes, we know that the amplitude of the sine curves is defined to be this this height, okay, or that height in terms of positive number. But there's also a peak-to-peak amplitude, which we rarely use in math classes, and it's basically double up. So the distance from the peak to the peak vertical distance called the peak-to-peak amplitude. But generally speaking, amplitude is this height. Okay. Uh, Now, uh, that's what it says. Amplitude is the maximum extent of the repeating event. Okay, peak to peak is just the double of that. I want to show you a different view of why we may be interested in look at the signals in terms of their frequency as opposed to their time. Now, here is an example of a signal that may have been picked up, a very clean signal may have been picked up by a transducer, maybe accelerometer or something like that. It's very nice and clean. The fact that it's nice and clean doesn't mean that it's not coming from a real life situation. Okay, so uh, this representation that you see here is the time waveform, but there is an alternative which is called in the spectrum form or frequency representation of this signal, which looks like that. Okay, these two they're coming from the same signal. One of them is showing something versus time, or the amplitude versus time. For example, this says millimeter per second, so this seems to be, for example, velocity that was picked up by the signal, by the sensor. And the same thing is represented in a different way. So these amplitude versus frequency. It tells you that in this clean signal, there's only two things, two participating a clean, maybe sine curve or cosine curve. We'll get to that in a minute. How do I explain what I just showed you? Suppose that we have two motors sitting on a table, and they're running at two different speeds, and one of them is at 50 hertz, the other one 40 hertz, and we have an accelerometer attached to this table, and it's picking up the signal. Okay. Now, let's pretend that the signal, this is turning at 40, this is turning at 50 hertz. So the signal that's going to come out, assuming there is no noise or anything, is going to be something like that. Okay? This is the time waveform representation. Now, we know that this signal is coming from two sources. One of them is a clean 50 hertz signal, sine. The other one is a clean 40 hertz sine. Okay. Of course, with different amplitude, the amplitudes are different because that depends on the amount of imbalance in the motor. Okay. The reason that we get these signals is because this motor has an imbalance, and if it's not perfectly balanced, ideal world, which will never happen. Okay, these signals will be the same height, but it is not. Okay. So what I've shown here is basically taking this sine form, this time waveform, and visualized it by whatever Fourier did. You know that fellow that I showed you the picture of? Whatever I did into two signals, 150 hertz, 140 hertz, obviously different amplitudes. Okay. So what you see there at the bottom is exactly the same thing that you see above it, except that I have added a third axis here. See this stuff? This red and green stuff is exactly that, except that I've added a third axis. And now I'm going to say, okay, same thing by the way. I'm going to take these two and shift them to the location on the frequency axis. There we are. For example, notice that the red one is shifted to the location 40 hertz, and the green one is shifted to the location 50 hertz. You can see that. It's the same thing, except that I've shifted these to a particular location. Now, if I look at this signal that you see on the right-hand side, not down the frequency axis. In other words, right now, if I look at it down the frequency axis, well, I'm going to see the original green and red curve sitting on top of each other. But if I look at a different direction, for example, I change my orientation and look at it down a different axis, such as the time axis, you're going to see this. Okay. And if you completely look at it from the side here, you actually to see two peaks. One peak for the red one, or one spike for the red one spike for the green one at location 40 and 50. And this is what we had as the frequency representation of that signal. Remember, I showed you those 3 slides ago, I showed you a, a, a blue curve, okay? Clean blue curve. And then immediately below it, I showed you two triangular spikes there. So that's where this is coming from. Those triangles were coming from. In that case, it was like that. There was a triangle here, and there was a triangle there. Okay, so let's look at some of the problems that we may encounter in this course. Let's model an airplane by breaking it up into lumped masses and springs. Okay, for example, you can view this several ways. The mass of the engine, we can pretend that it's a lumped mass here, but it's not. Obviously, it's not a point mass, but we can view it like that. Same thing on the left-hand side. Doesn't matter. And then in between the fuselage and this lumped mass, there is the part of the wing, and that acts like a fancy spring, isn't it? Fancy spring, because after all, what is a spring? You apply a load, it's going to deflect. What is a spring? It creates a resisting force for the motion of that mass. The same thing here. I mean, here I don't have an engine on the right side, but the wing on this side, the part of the wing on this side can be has a mass. So we can think about it as having a mass there. Okay, now and again, this portion of the wing also this portion of the wing also acts as a spring. Now I'm going to ignore damper here because we're not looking at damping yet. So essentially, I can look at the motion of this engine in the middle, ignoring the stuff on the right hand side of it, for example, as the motion of a mass and a spring. Okay. So this actually, right now, the way I drew it, may be too complicated to look at. So what we are essentially approximating that complicated setup where you have aircraft, engine, wing as a simple, for example, a simple mass and a spring. This becomes replacing the motion of this the mass here as a single degree of freedom system. We'll come to those things later on in detail. Okay. Uh, let me go back to my previous slide. Okay, I'm sorry, it's right there. All right. So what you see on the right hand side is saying that I'm interested. Notice that this mass, for example, whether you look at this or the other one, has motion up and down, right and left, and even torquing. Okay, but in a very simple approximation, I'm going to say, assuming that we're going to assume, for example, the motion is only up and down. Obviously, we pay a price. So it's a very crude model, but anyway, we can ignore motion, for example, to the right and torquing of this mass, and therefore only look at up and down motion. As I said, we pay a price, the model is not going to be as accurate. Uh, if you look at a car, and those of you who have taken vehicle dynamics class have gone through this, and you can replace the car, which is very complicated, okay? For example, as a quarter model representation of the car, where you have uh, everything in the car, including the mass of the compartment, the mass of the engine, the mass of the and the springs in the suspension is still represented by situation like this. This, as it is right now, it's a uh, you can think about it the way it is a 2 degree of freedom representation of the whole car, vibration of the whole car. Or you can look at it in this fashion. This is called the bicycle model. In other words, you have collapsed the right and left wheels, etc., but the front and the wheel are modeled separately. So this is a more refined representation of what you see on the left-hand side. Or you can do the whole shebang as, with four suspension, etc. Of course, you get what you pay for. The one on the right is more sophisticated, the one in the middle, and the one in the middle is more sophisticated representation of what's here on the left-hand side. In real life, these are okay for design purposes and people use it on a very regular basis. However, at some point you're going to have to do some finite element analysis in order to get more accurate version of the modeling of the entire car. Okay. Now, uh, let me show you this. Remember, I said that a uh, a vibrating system in its simplest form can be modeled as a mass spring and, of course, a damper system, but we're not talking about damping here. Okay. So for this vibrating mass, uh, uh, if you do it like that, I'm assuming that things do not torque, okay, all right, do not torque in the other two direction, because keep in mind, a rigid body has 6 degrees of freedom, okay? A rigid body in space has 6 degrees of freedom, three translation and three rotations, okay? And if we restrict the motion in a specific plane, for example, motion of that rigid body, then the number of degrees of freedom are reduced. So here, uh, if this is if this is moving only uh, in the plane that you see, plane of the screen that you see, and uh, you have two translations and one rotation. Okay. Uh, yeah. I mean, if you take away the rotation about the y-axis, of course, obviously the problem is going to be simpler, and that's also legitimate, and we're going to do a lot of that later on. But anyway, the number of degrees of freedom of a system, in a loose sense, whatever that number of degrees of freedom means, is determined on where in space this is moving. Okay. Now let's go back to that wing situation. We can ignore the fact that there is this piece here, ignore wing mass 2, and just concentrate on the spring here in the middle, and that this becomes a single degree of freedom system if we assume only it goes, for example, up and down. Uh, uh, but if you also want to include the mass here, which is going to be a more refined analysis, then this becomes a 2 degree of freedom system, okay? Because there are two masses, and these springs are not, by the way, none of them are rigid, okay? So uh, the more refined analysis would be look at the wing and model it as a 2 degree of freedom system. Once again, I'm talking about these degrees of freedom in a very loose way. You already have an idea what that thing means because you're taking machine dynamics, okay? But let's leave it like that, because in the next lecture, we're going to be more precise about what actually degrees of freedom mean. Okay. So basically what you see here is modeled like so. Okay. And of course, uh, if we eliminate some of these motions, some of these motions such as torquing, etc., then it becomes a true 2 degree of freedom system. But right now, it's not. Now, uh, we're going to be discussing uh, like what you see here actually is the simplest representation of a mass and a spring, a vibrating system. Notice that I've said that there's only 1 degree of freedom, motion in that plane downward, okay? No twisting, no sideways motion, etc. So this is a single degree of freedom system, okay? It is possible to model this thing with more degrees of freedom and you get more information. However, we're going to wait for that until next lecture. Okay, so if you want, if you want to see some very good videos, YouTube videos, these are the ones that I suggest on vibration. This one at MIT by Kim Van Diver. But this is a course in dynamics. It's only the last perhaps 3 4 weeks, 3 weeks of it is devoted to vibration. It's very good. Another one here at University of Akron by Dane Quinn, very good. and finally by Carmen Mueller at Florida International University. These are very good in case you want to see some more sources. Okay. Now, in a I primarily use, at least the designated textbook for this course is the Inman's book. Okay, it's not a requirement, but uh, this is a designated textbook. But there are some additional textbook in case you ever want to go to some other sources, and they're listed here. It's entirely up to you. Okay. Now keep in mind that the exams are open book, open notes. Bring anything you want in the hard copy form. Okay. If you feel like it, other books if you want. Now, I want to point out that this is not a math class. However, there is no way to get away from the math. The math is not advanced. It's the basic differential equations course that you took in your second year for part of it, not the whole thing. And some linear algebra towards the end of the course, the last 3 weeks of the course, where we do multi-degree of freedom system. Okay. Uh, Now I didn't have a chance to go through this thing in the class because we discussed the course syllabus, but and I told people that I'm going to put the rest of this presentation in the form of in the video recording. Okay. So I want to remind you that one of the most common equations that you solve in your differential equation was second order linear constant coefficient problem. Now, what does that mean? So stuff like this. Now notice that these are three different cases, three different equations, but the only difference between them is that the numbers are different, the coefficients are different. See, second order, because there is uh, two dots involved here, two derivatives, okay? Linear, because I don't have x double dot squared or I don't have x times x dot, etc. It's a linear differential equation. And constant coefficient. The coefficient in front of these numbers are constant. 1, 3, 2, 1, 4, 4, etc. Now, these things you spend about 3 weeks, 4 weeks in your differential equations course to solve them. Okay? These are called linear second order differential equations. And why are these important to us? Because at the end of the day, we are dealing with a dynamics subject. It's Newton's law applied, force equal to mass times acceleration. What is the acceleration? It's x double dot, or second derivative of position, for example. Okay? All right. Now, and in this case, if you say, okay, F equal to MA, so F equal to mx double dot, so where is the F? Well, in this case, it's a free vibration, so force is zero, okay, but doesn't have to be. Now, when you did this thing, at some point you came, you said, okay, yeah, there are dots here, I understand, but I have to solve a quadratic equation. You don't get the impression that this x is the same as that x. It is not. I should have called this thing maybe lambda or something. But anyway, so everybody knows from high school how to solve that equation. Either use the formula or factor it out. Okay, no problem. And this thing that you see here, or these things that you see here, let me go to the next slide. This single degree of freedom mass damper system, its equation of motion is right there. Oops. Mistake. Dot, dot, dot. Oh my God. I didn't realize that. Dot, dot squared. Cx dot k. I really screwed this up. Okay. Or at least this turns into that, but the equation is actually mx double dot plus cx dot plus k. Terrible. Okay, so it is possible to use this formula where A is M, B is C, and this C is K. It is possible to do it, and if you do it and massage it, you're going to get this form of that solution, the solution to this equation, not the differential equation, but this equation, which is going to be like that. Don't worry about that. This was a bad slide. Let's go to the next one. So look at some examples. Okay, let's take the first. And I'm really sorry for this last slide. It was terrible towards the end at the bottom of it. But anyway, let's look at our first equation. X double dot plus 3x dot plus 2x equal to 0. So your math prof said, you know what? Why don't we look for a solution like that? You might say, well, how did that math prof know? How do I know I have to go from here to there, assuming that x is equal to that? Please note that we are reaping the benefits of those pictures that I showed you, the people in those pictures, okay? And there are centuries of hard work that has led us to knowing this. Let's look at a solution of that form. Okay, so it's not a guess. It is not a ingenious guess. Lots and lots of people with a great deal of talent and intelligence worked over centuries to get us to where we are. So let's look at a solution like that. Okay. All right. I have x dot here, so I'm going to differentiate this thing. S is a constant. We don't know what it is, but you differentiate, you get s e to the st. You differentiate this thing again, you get another s, you get s squared e to the st. So we take all these three and stick it into that differential equation. Notice that they all have a common factor of e to the st that I take out. But if this product is 0, e to the st is never 0. So it must be that this parentheses must be 0. And this is where I said high school comes in the picture. And this one I can use the formula for quadratic, or just factor it out. And you're going to get two solutions, or two values for s. So we guessed the solution to be of that form. We came out with the conclusion that s is either -2 or -1. Okay, so one solution is like that. Believe me, if you take this and stick it in the top equation, you get 0 equal to 0. And the second solution is the same thing with the value of s being -1. And once again, you can try it yourself. Now, because this is a solution and this is a solution, both are solution, we can confirm that. And we are dealing with a linear equation. We know from either by direct checking or from superposition that the combination of them is also a solution. In fact, any multiple of the first solution plus any multiple of the second solution is also the solution to that equation. So that's what we call the most general solution to this differential equation. Okay, this is what you did for 4 weeks in your differential equations class. Now, and if you don't believe me, take this and stick it in there, you get 0 equal to 0. Okay. If we plot, depending, now remember, C1 and C2 depend on what your initial condition is. Okay, for example, you might say, what if x at 0 is 5 and x dot at 0 or x derivative at 0 is 6? Then you write those equations, plug in 5 here for t, and then differentiate it, plug in here, t equal to 6, for example, for t, you get two equations and two unknown, C1 and C2, work it out, and you get the solution. So the solution to this equation, that equation, depending on the initial condition, there are three different type of initial conditions given here, is something like that. The solution dies as time goes on. X of t dies as time goes on and on and on. Okay? Good. Perfect. Let's go to the second equation that I had in my list. Remember I had three of them? I said they're different depending on what the coefficients are. Okay? But they all look the same. Once again, look for a solution of this type. I need x dot, so differentiate it. I need x double dot, differentiate it again, and you're going to get that. take these three and stick it into that equation. There is a common factor of e to the st. Take that e to the st out. Okay, right there. This product is 0, and e to the st cannot be 0, so this parentheses must be 0. Either use the formula for quadratic, it's high school, or factor it out, once again high school, and you're going to get, oh, S1 equal to minus 2 and S2 equal to minus 2. Remember, in the previous case, S1 and S2 were different numbers, but not here. They're the same numbers. Okay, so one solution is right there, because that's what S was. S is minus 2. You plug in minus 2, you get there. So what's the other solution? It's no good to put this thing back in there again. Say the second solution is minus also e to the minus 2t. Well, these are not different. Your math prof told you, showed you, made you, convince you that the second solution is actually this times t. And if you say why, try it. Remember those pictures, 400 years, 300 years, is taking us to this location. You don't believe it? Take this, plug it in. So first solution is there. Second solution, just multiply it by 2. Now, these are called, these are solution. The general solution is a combination of 2 from the method of superposition, because we're dealing with linear differential equations. Good. Now, what are these C1 and C2? Well, depend on the initial condition. If you give me 2 initial conditions, for example, x at, just hypothetically, 0, and x dot at 0, I can write those equations, solve 2 equations to unknown, find C1 and C2. But if you do that, you're going to get a behavior like this. Once again, solution dies as time goes on. I mean, it could stay above the axis, it can stay below the axis, like that. It can cross the axis, but it will not oscillate. Okay? So this was the second case. All of these things are going to come up in real life when we do vibration problems. This has nothing to do, at this point, it looks like just a math class. Fine. Let's go to the third one. Oh yeah. Third one. This guy is going to pop in. Third case. And in a sense, you will need something called Euler's formula. Remember in high school, somebody told you e to the theta equal to cos theta plus j sine of theta? Or even in university, I'm sure you have seen this thing, but either in the math class, so let me go back here. Okay. Yeah, you're going to see that either in the math, either in the math classroom, you have seen that, but even in your engineering courses, you might have come across e to the theta equal to cos theta plus j sine theta, or you may have called it I sine theta. And everybody says, this is true. It is true, but this is not an elementary concept. We're just feeding you something that 400 years, 300 years has taken us there. Okay. Anyway, I'm just saying that this is what's needed to do the third case. Now, I'm not going to go through this business of, square root of minus 1, etc., but I'm telling you that this is what's needed in your third case. Okay. Where's my equation? That was the third equation, which I forgot to write here. And I'm sorry, I forgot to write down the equation. It must have been x double dot plus 4x dot plus 5x. That's what it was, the third case. X double dot plus 4x dot plus 5x. So I've taken these and I put them in that equation and factored e to the st, and there we are. Now, e to the st cannot be 0, so it's this piece that's 0. solve it or factor it, that's where the solution is going to be complex. There. Most of you are going to have a hard time factoring this out. Just stick it into that formula from high school. Minus b plus or minus square root of b squared minus 4ac, etc. You get this, and you get one solution, second solution. Complex. That j is the square root of minus 1. Now, the question is, what do I do next? Well, x1, you just plug it in. You just plug it in right there. Remember, S1 is right there. Just plug it in. And use the Euler's formula right there. Euler's formula. Now remember, when you look at this, e to the minus 2t is just a real number. E to the minus 2t plus uh, plus t, jt, right? So e to the minus 2t is just a real number. I just took it out. But e to the jt remains there, and e to the jt is right there. Euler. Same thing with x2. Same thing. And if you use Euler's formula, because the top is e to the minus jt, then you have to put a minus t here, and using properties of sine and cosine, it reduces to that. So x1 is right there, x2 is right there. Now, the general solution is a combination of these two, okay? Except that because we're dealing with real numbers in our problems, okay? You can, for example, you can just take the real part of this and the real part of this and the complex part of that or imaginary part of that and just use that. Okay, same thing here, because notice that the real part of this is the same as the real part of that. The imaginary part of this is the same as the imaginary part of that. So essentially it's the combination. If you don't believe me, take this stuff, stick it in there, you're going to get 0 equal to 0. And if you plot that, you're going to get a curve that is dying down. X is dying down as a function of time. Oscillation. Vibration. Now, if there was no damping, that middle term, remember that there was x double dot thing plus something times x dot plus something times x. Remember that? If that middle term was not there, the x double dot was not there, that means the coefficient of x dot is 0, then we don't have any damping. Okay? And if there's no damping, this will not die down. It just oscillates forever, up and down, up and down. And that's your vibration. Now, remember, I said that this is not a math class, but these things are buried in a vibration, in the vibration subject. And I'm just showing you the elementary stuff that's buried there. There's a lot of complex math math that is complex math that's buried in there. But at a level like this, at the first course in vibration, we don't touch those. But these basic ones are not going to go away. You have to know that. Now, folks, listen. You and I did this thing in class. It took another 20 minutes. Okay. Part of it is because I did the course syllabus, etc. So ordinarily the lectures are about 1 hour and 15 minutes, something like that. But because I'm recording these, the recording, a lot of the pausing and things like that, and asking question interaction with you folks, it may become shorter. But in the class, it took 1 hour and 15 minutes. Okay. All right, so our second lecture will be also. I mean, these are all. I do my best to record these things and post them on YouTube. I want to remind you once again that you're welcome to take notes, to screen capture anything that you see here in my presentation and bring it to as a hard copy form on the exams and quizzes and things like that. But I will not provide you with the slides, and this is by design. It's not want to. I don't want to make life hard for you. It's just that I feel that if you cannot commit yourself to take notes of the things that you don't understand or you need, you don't have to take notes of everything, whether it's by coming to class, taking notes, or whether by watching these and taking notes, or whether by screen capturing these and bring everything that you want, I don't see an obligation to just give you the stuff. It's not good for you. I can guarantee you that. I'm pretty sure some of you disagree with me, but that's okay. See you on Thursday.